Okay, we're going to do another proof by induction on lists. So here I've given you a new function. This function is called length. It takes in a list of type A and returns an int. How length is defined? The length of an empty list is 0, and the length of an element bolted onto the front of a list is 1 plus the length of the list xs. So the length of x cons xs is 1 plus the length of what's left over after you throw away the x. Okay? We're going to prove the not so interesting property that for all lists xs, the length of any list is always greater than or equal to 0. Okay? So how do we do this? Well, we start with the base case. So the base case here, there's only one variable to induct over, so I'm going to induct over xs. I'm going to prove for xs is equal to empty. So we need to prove that the length of the empty list is greater than or equal to 0. Okay? So we start with the left-hand side. So length of empty, which by definition is equal to 0 by L1, which is greater than or equal to 0 by math. Okay, that wasn't too bad. So now we have to prove for the step case. So the step case, I will assume the statement to be true for some arbitrary list ys. So I'm going to assume length of ys is greater than or equal to 0. And denote that as the inductive hypothesis. And then I want to prove for any new element y, the length of y cons ys is still greater than or equal to 0. So I'll start with this left-hand side. So the left-hand side is equal to the length of y cons ys, which by the definition of length is equal to 1 plus the length of ys, 1 plus length ys by rule L2. And then I can use my inductive hypothesis here. The length of ys is greater than or equal to 0, and that means 1 plus the length of ys ought to be greater than or equal to the 1 plus 0. Right? The sum of two terms here is going to be bigger than these two terms here, because this single term here is bigger than this single term here by inductive hypothesis. 1 plus 0 is 1, and 1 is greater than 0 by math. Okay? Prove for the base case, prove for the step case. Therefore, for any list xs, the length of xs is greater than or equal to 0. Okay? So deliberately easy problem as a warm-up. I want you to now prove the trickier problem. So I want you to prove that length distributes over concatenation. So what I mean by that, I want you to prove for any list xs and for any list ys, the length of the two lists concatenated is the same as the length of the first plus the length of the second. Okay? So have a go at proving that, and then we'll go through the solution afterwards.